Hi everybody. In this video I would like to show you how the capacitor can be charged and how the capacitor can be discharged. And also guys, I will show you the time, the required time for the capacitor to be charged, and also the time for the capacitor to be discharged. So let's start to charge the capacitor. So what do we have here? We have a capacitor right here. It is 22 microfarad, and we have another device here which is resistance. So this resistance is like around 1 mega ohm. So let's get started right now and try to connect the circuit with the DC supply. So let's see what do we have. I will start the time when I start connecting the circuit, and you can look at here and there, so you can see the time. So I will do that. I can do that simultaneously, but I will try to do it simultaneously. The power supply wasn't connected. I will connect the power supply to the electricity. So now the power supply is connected. So hopefully it works right now. I will try now to connect. Yeah. So let's see what's happening here. So you can see that the voltage is dropping down. So why the voltage is dropping down? Because the capacitor is charging. So once the voltage achieves like around 0, we will stop the stopwatch. You can see that, so it is dropping now. The voltage is 6, yeah, and then 5, yeah, 4.9, 4.5. okay, it is dropping right now. And why the voltage is dropping? The voltage is dropping because the capacitor is charging. And once the capacitor is full charged, the voltage will be around 0. Let's continue. Yeah, so what do we have? We have around like 1 minute. That required around 1 minute. We will continue until we have around 0, so 1.8, 1.7, 1.6, 1.5, 1.4, let's wait, and 1.3, let's see, 1.2. Great, so focus here, guys. You can see that the voltage is still dropping down, 1.1. Okay, so we have 1 voltage. So 1 volt, the voltage is 1 volt right now. Actually, I'm measuring this voltage across the resistance. Yeah, so we can see that the voltage is dropping down. And here you can see that we have 2 minutes here and 24 or 25 seconds. Let's continue to wait for some time until we achieve 0 or close to 0. So 0.8. So we have 0.8. Okay. It should continue to drop, so 0.7. We can change the voltage to be here, so that looks accurate. So we can see here, so we have 0.792, yep, 78, yep, so it's dropping right now, guys. You can see that 0.7, and here we have around like 3 minutes. Yep. and we will compare the required time for the capacitor to be charged and the required time for the capacitor to be discharged, and then we will compare them. So this experiment, guys, can help you to see and visualize what I gave you last session. I know that last session was a little bit hard to be understood, and that's why, guys, I created this experiment for you, just to show you what's happening. Yeah, so don't care about this minus sign, because I need to reverse these two terminals here, but don't care about it right now. Yeah, so that's good. Yeah, so it's still dropping, just needs longer time. We can't consider this as a zero, but if we achieved, for example, 0.4 or 0.3, that would be great. So that can be considered as zero. So, and you can see here that the voltage still dropping down and the capacitor still charging. Yep, let's continue to watch, and here we have like 4 minutes 46 or 47 seconds. Continue. Yeah, and we will have this experiment explained in details when we do this week lab. So in this week lab we will study the RC circuit. So in today's lab we will study the RC circuit, and I will show you guys other details in this experiment. But for now, just I would like to show you how the capacitor is charged. Okay, so yeah, it will take a longer time. So what I can do now, guys, so I will stop. So let's consider this time. So what do we have here? So the capacitor took 5 minutes and 43 seconds to achieve 0.6 volt. So for 0.6 volt, yeah, so like the remaining voltage for this capacitor to be fully charged was 0.6, and this is the time, the required time for the capacitor to be charged. So here we have 5 minutes and 43 seconds. That's great, guys. So this is the time for the capacitor to be charged, 5 minutes and 43 seconds. So that's great. You can see here that the voltage is still dropping down. We will have this in details when we do today's experiment, but for now, guys, we need to learn and we need to know how to charge the capacitor and how to discharge the capacitor. So what I want to do now, I need to disconnect the circuit from here and disconnect this from here, and now I will have the resistance and the capacitor just in one loop, and see what will happen here. Okay, so I need to start now. So the capacitor is discharging now. You can see that the voltage is dropping down. I was a little bit late to start the stopwatch, but that's fine. But you can see that the capacitor will just needs short time, like shorter than the required time for the charging process. You will see that, guys. Let's see. So here we just have like 36 seconds, and here we have 3.4 volts. Let's continue. Let's continue now. We have 2 volts, so that's great. It's still dropping right now, so we have 1 minute, and here we have like 1.34, 1.2. Yeah, so what I would like you guys to do, just to practice for this week lab, to plot time versus voltage here. Try to do that, guys, and see what will happen. Yeah, try to do that and see what will happen here. Great, so it is dropping. It is around 0. Let's see here. So to achieve 0 volt, so how long time do we need? Okay, you can see that the voltage is still dropping down. So here we have 2 minutes, just 2 minutes to achieve 0.3. We didn't do that with the charging the capacitor, but look at here. During the discharging process, you can see that the voltage is dropping fast, and here we have 2.17. So 2 minutes and 17 seconds. I will wait for some time and see what will happen here. So that's great. That's great. That can give you guys kind of sense what's happening when we discharge the capacitor. Yeah, so that's great. Okay. So we have 0.15. Yeah, it should be around 0. And you will see that this time should be like shorter than the time that was required to charge the capacitor. 0.12. Wait for some time, maybe we can change the scale to see that clearly. Drop. Okay, yeah, so now we have around 0. So yeah, approximately. So to achieve around 0, we consumed 3 minutes and 49 seconds. So you can see the difference here, guys. Hopefully this experiment helped you guys to understand how to charge the capacitor and how to discharge it, and also the required time to charge the capacitor, as well as the required time for discharging the capacitor. Thank you so much, guys. Right now let's continue the session. Thank you. Hi everybody, I hope that all of you are doing well. So today we will do lab number 5, and in lab number 5 we will study charging and discharging the capacitor under AC power supply, or under alternating current. Yeah, and you know, this is the function generator. We studied the function generator, and you have some background from lab number 4 about the function generator. Also, guys, you know the oscilloscope. So the oscilloscope is not like complicated equipment. It is just a tool that can help us to measure the voltage and the frequency, or the periodic time. So that's great. So you know all of these equipments, guys. What we will need some coax cables to connect the circuit. We will need the resistance. This resistance is 150 ohms, and we will need capacitor. So this capacitor has capacitance 22 microfarad, so we'll use it as well. And I will show you guys the 22 microfarad, so you can find it right here. Yeah, so 22 microfarad, and this resistance is around, should be 150 ohms. Yeah, 150 ohms. Hopefully it is clear. Yeah, so now let's connect the circuit, and the circuit should be, guys, like this. So it should be like this, guys. What do we need to have? We need to have a capacitor connected in series with a resistance, and then connected to the power supply. So the voltage across the resistance is VR, the voltage across the capacitor is VC, and this is V peak to peak, which is the power supply or the function generator voltage. So let's start connecting this circuit, guys, and see what we will have. Okay? Yeah. So to connect the circuit, we need to use those cables. So I will connect one of them to the power supply, as you can see right here. And by the way, the power supply has 30 hertz. So this is 30 hertz. So hopefully that's clear. This is the frequency from the power supply. Okay, so let's connect the circuit and then see what do we have. Okay, so first we start with the resistance, as you can see. So the resistance is connected, as you can see, and then from the resistance we need to go to the capacitor. So this is the capacitor, and then from the capacitor to the function generator again. So hopefully it is clear, guys, for you. Okay, I will remove this so you can see the circuit. So resistance and capacitor. The other way that I can use to help you to distinguish between the capacitor and the resistance, I can use some labels. So these labels can help you guys to distinguish between the capacitor and the resistance. Yeah. So, and then I will try to indicate that this is a capacitor, so hopefully it is clear. I will try to adjust and zoom in. Here is the resistance. Yeah. So resistance and capacitor, resistance and capacitor. 150 ohms, 22 microfarad. So now what we will do, guys, we will try to measure something called the time constant. So what is the time constant? The time constant tau, guys, can be found from here. I will show you that. So, you know guys, as I mentioned, so you know, as I mentioned guys, we have this circuit, capacitor, resistance, and power supply. So what we will do to figure out the time constant, so the time constant can be measured if we applied one of the Kirchhoff's laws. You still remember guys lab number 3. So in lab number 3 part 1 you studied Kirchhoff's laws, and what I will do guys, I will sum up these voltages. So VC plus VR is equal to V peak to peak. So this is Kirchhoff's law. So the voltage across the resistance and the capacitor is equal to V peak to peak. If we removed the power supply, what will happen? The thing that will happen is that VR plus VC is equal to 0. So this is equation. VR plus VC is equal to 0. I mean if we remove this power supply. So the equation will be like this. So the equation will be like this, guys. So this Q over C, this is VC, or the voltage across the capacitor. We studied that the voltage across the capacitor is equal to charge divided by the capacitance, plus IR. So IR here is equal to the voltage across the resistance. So I is the current and R is the resistance value, and that's equal to 0 since V peak to peak is equal to 0. Now guys, I will try to modify a little bit this equation. So we know that the current is equal to the first derivative of the charge with respect to time. So that means we can write this term right here in this form, R dq over dt. So that's great, plus Q over C. So we still have Q over C right here, which is from this term right here. So the whole thing here is equal to 0. Now we can use differential. I know that you don't have any experience about differential equations, but the solution for this equation right here is equal to a exponential minus t half over RC. So the solution here is a Q. So Q here is the solution for this equation. So what does that mean? That means if we use this solution, we will have 0. So this equation will equal to 0 when Q is equal to A e exponential minus t half over RC. T half here, I will show you how to get t half. RC here is the goal from this lab. So in part number 1 of today's lab, we need to get RC experimentally. And RC, guys, here is equal to time constant. And the time constant here is called tau. So tau is equal to RC. I will show you that. So tau, the time constant, is equal to RC. This is what we are looking for. So that's great. So let's now learn how to get t half from this experiment. So to do that, we need to start working on this experiment. So let's get started. Okay, so As you know, guys, the value of this resistance is 150 ohms, and the value of this or the capacitance from this capacitor is 22 microfarad. So what we will do, we will just apply the equation that we just have learned, which is tau, the time constant, is equal to R, the resistance, times the capacitance, which is 22 microfarad. So I will show you that from this equation right here. So tau is equal to RC. So I will write that down. Maybe that's easier for you to recognize. Yeah. As we learned, tau, the time constant for this RC circuit, is equal to R times C. R is the resistance and C is the capacitance. So R here is 150 ohms and C is 22 microfarad. So to get the time constant, we need to multiply them, so we can get like 3000 or 3300 microfarad times ohm. Yeah, so I'm sorry for that. And then, guys, we can change this unit to be second and try to adjust this number here, which is 3300 micro, to be 33 times 10 to the power minus 4 seconds. Also, this number can be adjusted to be 3.3 millisecond. So 3.3 millisecond, guys, is the theoretical number. This is the theoretical number for the time constant. So what I will do right now, I will try to get this number experimentally. So what I will do, I will use equation, and I will show you this equation, guys. I will go back right here. Yeah, I will use equation, guys, and this equation will have t half and the time constant, which is tau, R times C, and another number, which is ln 2. So you are not required to derive this equation, but it is a good idea to know this equation. I will write it down for you. So this is the equation that I mentioned, guys. So we have tau, the time constant, is equal to R, the resistance, times C, the capacity. And that's equal to t half. I will show you how to measure t half, divided by ln 2. So as I mentioned, you don't need to derive this equation. Just you need to know that the time constant for the RC circuit is equal to resistance times capacity, and that's equal to t half divided by L2. This t half will be extracted using the oscilloscope. So how to figure out t half? This is the question that I will explain to you. So here we have a y-axis. A y-axis represents the voltage, x-axis represents the time, and you can see that we have this kind of wave. So it's not a triangle wave, but you can see this shape right here. So this is the output. This is the output voltage across the capacitor. What about this dashed wave? So this dashed square wave represents the input signal. So this squared wave represents the input signal, and this signal that you see right here represents the output signal across the capacitor. So t half can be measured by dividing the voltage amplitude by 2. So when we divide the voltage amplitude by 2, so we will have this much right here, and this number right here is corresponding to time value right here, and this time value is t-half. So by knowing this time value, we can go to this equation right here again. So we know that tau is equal to t-half divided by L2. So by knowing t-half, we can figure out tau experimentally. And I showed you how to figure out tau, the time constant, theoretically. So let's go ahead now and do this experiment. So what we will do here, we will have the RC circuit, and we will try to figure out tau from here. The resistance that we have right here is 150 ohms. So 150 ohms from here. Okay, so let's go ahead now and read t-half from the oscilloscope. Okay, so hopefully the oscilloscope monitor is clear. Last time you mentioned that you couldn't distinguish the signal from the oscilloscope, so I attempted to have or to zoom in to the oscilloscope screen. So this is what we have. So this signal right here was the voltage, peak-to-peak voltage across the capacitor. I will show you that. Maybe I can move the camera and show you what I'm doing here. I'm measuring the voltage across the capacitor, and this is the resistance right here. So the resistance is right here, and this is the capacitor, and we are measuring the voltage across the capacitor. Let's go back now. Okay, now what we will try to do, we will measure t-half. So to do that, we need to expand the time division like this. Okay, and you can see that the peak-to-peak voltage is 1 square, 2, 3, 4. So we have 4 squares times 5. So that means we have 20 volt peak-to-peak voltage. What I will do, I will target the 0 voltage right here. So this is, this is the region that we are looking for. We need to go to the 0 voltage, which is right here, and then count how many squares do we have. Actually, we can see that we have just 1 square. So this is 1 square from this point to that point. So this is 1 square. So 1 square times 2 millisecond. So that will give you 2 millisecond. So this is t-half. So t-half is 2 millisecond. And this t-half right here was measured, so I will write it down, was measured with 150 ohms resistance. So t-half is equal to 2 millisecond. Yeah, so this is t-half. Okay, so it is 2 millisecond. Now what I will do, guys, I will move or remove the 150 ohms resistance and replace it with 118 ohms resistance, and see what will happen to the to t-half. Okay, so we'll try to adjust this a little bit. Maybe we can increase this. Yeah, so what we have here, we have 1 square. Always we need to come here to the 0 voltage and then count along the time axis. So we have 1 square and then 1, 2, 3, 4, 5, 6, 7, 8. So we have 1.8 times 1 millisecond right here. So that will give me 1 millisecond. So t-half is 1 millisecond. So t-half is equal to 1.8 millisecond. Okay. Now I will remove this resistance, which is 118 ohms, and replace it with another resistance which is smaller, has like smaller value. It is 59 ohms, and see what will happen. So with 59 ohms we have something like this. I will always use the oscilloscope to try these knobs right here to try to adjust, and see what do we have. So what we have here, we have around 1 square. So here we have 1 square 0.2, if that's clear for you. I will zoom in like this, maybe that can help. So you can see here we have 1 square 0.2, so 1.2, and that times 1 millisecond from here. This is the time division. So 1.2 times 1 millisecond time division, that will give me 1.2. So t-half became 1.2 millisecond with 59 ohms. So that's great, guys. So in the worksheet you will find the table, and you need to fill this table. So what do you have in the table? You need to write down t-half, and after you write down t-half in the table, you need to figure out tau. So how can you do that? How can you figure out tau? So by knowing t-half, you can go to this equation. So we can see that tau is equal to t-half divided by ln2. Okay? So you need to divide t-half by ln2 to figure out the time constant, which is so you can see that we have the t-half values here for several resistors that we used, so you can include them as well. So that's great. This is one part, and also I would like to show you. So we are done with the first part, which is great. Now what I will do, I will try to show you what will happen to this signal if we used resistors with higher values. So let's see what will happen. So I will change now this resistance, okay, which is 59 ohms. Okay, and before that I will zoom in again like this. So I will use 1 kilo ohm and see what will happen. So I will connect the 1 kilo ohm, and I would like you to look at here. Do you have the same shape? So the signal does the signal has the same does the signal have the same shape that that it had with the 59 ohms? So what do you think? I will go back to the 59 ohms so you can see the difference again. Yep, look at. So this is the signal with the 59 ohms. So I will remove the 59 ohms and use the 1 kilo again. Okay. So this is with 1 kilo. It is like this. Just I would like to describe what you see right now. And I will use now 10 kilo ohm. So let's use 10 kilo ohm and see what will happen. So this is with 10 kilo ohm. So the signal is very, very small, as you can see right here. Yeah, so you can see here we have like 50 millivolt right here. So it's very small. I will now remove the 10 kilo ohm and then try to use 1 mega. So this is 1 mega ohm. Let's use 1 mega ohm and see what will happen. Yeah, so there is no signal at all. Yeah, so we can't. Yeah, maybe like very, very small signal right here. So I would like to write down what you can see when we added resistors with the higher values. Now I will go back to the 150. Yes, so let's go back to the 150. Yeah. So this is the nice signal that we can receive from the capacitor. Okay, so this is part number 2. We are done with part number 2. Now we will move to part number 3. And let's see what we can do. So this is part number 3, and as you can see here, we are feeding this RC circuit with AC signal, and you can see that VP is 10 volt, and from there we can see that V peak to peak is 20 volt. The frequency that was applied to this circuit was 30 hertz, like 30 from 30 to 29 hertz. Now what I would like to do, I would like to increase and decrease the frequency, and I would like to watch here and write down what you can see when we increase the frequency, for example, what we can see when we decrease the frequency. So let's do that. Increase the frequency. So what you can see here, just write down what you can see. Increase the frequency, increase the frequency. Yeah, so what you can see, and then I will decrease the frequency again. Decrease the frequency, decrease the frequency. Maybe I can go to lower frequency. Like around 1 hertz. So you can see what we can get with 1 hertz. We can get something like this, but when we increase the frequency again and then adjust the oscilloscope, so we can go back to the same signal that we have before. Let's go to 30 hertz. Yeah, around 30 hertz. Yeah, so you can see that we have this signal again. Just I would like you to write down what you could see when we increased or decreased the frequency. Yeah, so that's great. This is everything regarding lab number 5. So if you have any questions, please don't hesitate to email me. I will post you the worksheet today. So try to go through the video first, and then try to answer the worksheet questions. Thank you so much.